So good morning to everyone. I wish first of all to thank the organizer for giving me the possibility to show older and newer results in our research group. And I was asked to make this tutorial on, let's say, coherent caloritronics. So I will try to explain to you in the simplest way possible what it is and what is the current status of this research. So let's see the outline. I will start with the indicating the motivation and the mission of coherence in thermal transport. I will try to give an overview of the main path that we are following towards this end, and I will introduce the basic concept first, the first stage of thermal transport in the Josephson-based quantum circuits. Then I will show how it's possible to realize double and single slit interferometers, balanced thermomodulators, that means combination of multi-loops heat interferometers. I will show towards the end the thermal analog of the electric pi junction, Josephson pi junction. And I will conclude showing a very last experiment on how to make a Josephson thermal router. That means a system that is able to distribute thermal currents among different reservoirs on chip. Okay, so let's start with the motivation of the mission. So, what is coherent caloritronics? Coherent caloritronics, from the Latin word calor, that means heat, is basically a pretty young branch of science, I would say, that deals with the complementary of coherent electronics in some sense. So it deals with the phase manipulation, mastering of heat transfer in a fully solid state environment. Okay, so the goal of the coherent electronics is to provide the original and novel approach to realize thermal devices from heat transistors, splitters, diodes, new kind of refrigerator, exotic quantum circuits that can take advantages of the above mentioned building block in order to increase further the functionalities. Then at the end, to address and to understand fundamental energy and heat-related phenomena at nanoscale. For instance, the question of coherent dynamics, the question of interference in heat, time dependence effect, quantum thermodynamics, the coherence, so forth. So, if we want to summarize in one statement, coherent caloritronics is the main goal is to develop quantum technology for managing heat in nanoscale circuits. Okay? So, what was done in the past? I want first of all to make a difference. What was done in the past and what is the main subject of interest of coherent caloritronics. So, if we go back 20 years ago, there was a lot of work in thermoelectric effects in Josephson junction, in particular in the group of Chernobylovka, Ryazanov and co-workers, where they were investigating both the DC and AC thermoelectric response of supernormal, super light Josephson junctions, so typically vanadium copper junctions. So as the word is saying, the thermoelectricity, they were studying thermoelectricity within the Josephson effect. So the electric response to a thermal stimulus in the system, okay? And they were also studying, for instance, the behavior in the presence of magnetic fields, showing a sort of oscillation of the thermal power as a function of magnetic field. So in those kind of junctions, they obtain thermal power pretty low, I mean, sizable, but still low with respect to more effective thermoelectric materials of the order of 10 to the minus 8 volt per Kelvin. Okay. Okay. So this is in some sense, it's thermoelectricity within the Josephson effect. What I'm going to show now has nothing to do with thermoelectricity. So is pure thermal transport. So it's not electric transport. Okay. So is simply how electric current flows in a Josephson circuit and a superconducting circuit according to a thermal bias of the system. So there is no electric bias in the system. And there is no electric response of the system. Okay, the system is fully without any thermoelectric effect. So let's start with this very simple cartoon to show what is the physical basis of coherent caloritronics. So if we look at the upper panel here, this cartoon, we see that the idea is to consider different reservoirs of perfect electron gases in a thermodynamical language, let's say. So as we are dealing with in a fully solid-state environment, our perfect gases will consist of electrons residing in normal metals, superconductors, semiconductors, and so on. Okay, so the idea is to have reservoir at different temperatures, and then to conceive suitable physical mechanisms that exploit the macroscopic superconducting phase in order to control the heat current J left and the right heat current J right flowing from the hot to the cold direction. Okay. So in this sense is coherent. So we are planning to construct a sort of research field where we understand how is possible, thanks to the macroscopic quantum phase, to control up to a large extent the heat flow in superconducting and solid-state circuits. Okay, so towards this end, we have chosen three different paths in order to three different approaches to do this. Okay, so the first one is based on the exploitation of the Josephson effect. As I will show, the Josephson effect has a very peculiar properties for which the thermal transport becomes phase dependent. Then there is another very important part that is related to proximity effect. What is proximity effect? Proximity effect deals with conductors that have acquired genuine superconducting properties through the intimate contact with the superconducting body. Okay, so in this proximity effect structure, it is known that the proximity layer, that is S prime in this case, has acquired some superconducting-like properties from this intimate contact, and these superconducting properties are very, very important in the sense they affect deeply the spectral properties of the metal from the electrical and thermal point of view. For instance, the density of states becomes phase dependent, the specific heat and the entropy, the superconductor of this engineered superconductor, becomes phase dependent. The electron phonon coupling, so the exchange of heat between the electrons and the phonons in the structure, becomes phase dependent. Okay, so in some sense, a proximity superconductor is a very ideal candidate because it can be engineered that will, thanks to the phase, in order to have a specific response to heat. And then there is the third one, the third method, that is control of thermal transport by tuning the electron-photon interaction. So to tune the electron, the interaction of the electrons in a metallic structure with the photons to the electromagnetic environment. Okay, so we can think of two different bodies, for instance, and two different resistors residing at different temperature, which are not in galvanic contact, for instance, and which are just interacting through a quantum structure. It is a resonator, for instance, in the form of a DC squid. Okay, so thanks to this coupling here, by changing the resulting impedance of this object here with respect to the magnetic environment, thanks to the flux, we can control how the two reservoirs can interact in terms of exchange rate between of the energy of one with respect to the other. And so this can be a very effective way of controlling the heat transport from one side to the other. Okay, so in this tutorial here, I will concentrate mainly on this part here, showing just some of the other two paths in order to give you an idea of what has been done and what is going on. Okay, so concerning the first approach, the idea is to use a Josephson tunnel junction, for instance, or more general Josephson weak links. And so the circuits are typically composed by, you see, there are some normal metals tunnel coupled together, and then one exploit or a double junction interferometer, let's say a DC squid, or for instance a single Josephson diffractor in the form of an extended Josephson junction. Okay, and then one typically bias at different temperatures the reservoirs, and then study how the heat flux is flowing in the system, as we are not, as the heat flux cannot be measured because it does not exist an ammeter for heat currents, what we are basically doing is our observable is the electronic temperature, okay, in the reservoir. So what we do is accurate thermometry to investigate how the temperature of the different systems in steady state on a dynamic situation are altered by heat flux flowing in the system. For instance, in this double junction interferometer, there will be a sort of expected squid-like behavior, like a conventional squid. When we have an extended Josephson junction, there will be a sort of diffraction-like Fraunhofer pattern if the junction is rectangular. So I will show some of the experiment later. Then, if we go back to proximity structures, for instance, so I was saying that they are very promising in the sense that we don't need a genuine superconductor to implement them. I mean, what we need is a material that does not possess any superconducting properties, but then is contacted. There is an intimate contact with, for instance, a superconductor. In this case, for instance, we have a normal metal here in the middle, or here is a superconductor, for instance, and it is laterally contacted by a superconducting ring. And thanks to this contact here, the suitable geometrical conditions, with the flux, we can control the amount, let's say, of superconductivity induced in this part here. So, and as I was saying, the density of states and other important properties of the metal becomes phase dependent in this case, okay? So, for instance, in this case, the electron-phonon coupling of the orange part of the proximized metal becomes phase dependent. So this is a nice way to control the rate at which our let's say, engineered superconductor can exchange heat between electrons and its phonons, okay, thanks to the phase. So this is a sort of knob that allows to control the amount of exchange. And for instance, another possibility is to use this proximity part here. If we contact this proximity region, whose spectral properties can be controlled thanks to the flux, to an additional normal contact in order to implement a sort of phase-tunable proximity thermal valve, no? So because the thermal conductance of this proximity metal, of course, depends, as I was saying, from the phase, and so the thermal transport between this S prime and N becomes fully phase dependent. What is nice in this kind of system is that in this sort of proximity valve, we can get a cutoff of a complete closing of the heat flow in the system. It's very equivalent to the spin valve in some sense, to an ideal spin valve, okay? Is a sort of ideal thermal valve in which heat can flow or can be blocked. Because, for instance, in the other cases, like for Josephson interferometers, we can just modulate the heat current in the system, but not completely close the heat flow. So this is the second approach. Let's go on the third approach, that is photonic heat transistor. Photonic heat transistor sounds also very interesting because, in some sense, we could think to implement a sort of wireless technology for managing heat. For instance, to cool at the distance of a body. This would be very important. So there are two reservoirs at a different distance, so one can cool a body at a distance without touching this directly. So this would be, for instance, you can imagine one could cool a qubit at a distance without touching. So to increase the coherence time of a qubit just by cooling at a distance. So up to now, there were a few experiments on this. The first one, I would say that the very first experiment in coherent caloritronics dates back to 2006 in the group of Jukka Pekola, okay, where they used exactly this photonic thermal transport and showing how two reservoirs and normal metal resistor, let's say, residing at different temperature, a sufficiently low temperature can exchange heat thanks to the coupling with the environment that is mediated by these two squids structures in parallel. So by changing the flux, you change basically the Josephson current of these guys here, so the Josephson inductance of these two objects here, so they can be treated as inductors, okay? And so by doing this, you change the impedance of the system, and so you change the amount of heat transfer from one part to the other. So you see that there are very nice temperature oscillation in the system from one part to the other, okay? Something similar can be engineered, for instance, by using a fully non-galvanic system, okay, a non-galvanic system. So this can be, you can couple, so this is a sort of completely wireless system. So it can be an inductive or a capacitive system. Recently, there was a work by Alberto Ronzani, still in the group of Yucca, where they use a capacitive coupling in order to implement a sort of fully photonic, non-galvanic valve, okay, thermal valve. Okay, so let's go a little bit to show how do we typically proceed in terms of experiments. As I was saying, the observable that on which we are concentrated is the temperature, okay, because we cannot measure heat currents in a solid system. There is no ammeter for heat currents like there is an ammeter for electric currents. So what we typically do is to measure the electronic temperature of a reservoir, and the basic assumption is that we can define the temperature in the system, okay? So to be defined the temperature, we need that the electron-electron interaction is sufficiently strong to thermalize a quasi-particle among themselves. And typically, the temperature of the lattice is sufficiently low that the electron-phonon coupling is weak. So we can create in the system a sort of quasi-equilibrium regime. So as yesterday it was already explained, the temperature that we establish in all these reservoirs is typically a quasi-equilibrium temperature. So we can define an electronic temperature that can be very well much different from the temperature of the lattice. So this is called typically a hot electron regime. Okay. In the opposite case, where we are strongly non-equilibrium, so when the temperature can no more be defined in a thermodynamic way, we can, of course, define distribution function in the system. And what we do is that with a suitable technique, a similar techniques, we can measure the distribution function of our quasi-particle system. So in that case, then it can be, of course, converted to an effective temperature to a sort of Sommerfeld expansion in order to understand what would be the electronic temperature if the system were in quasi-equilibrium. But typically, what is known is that at least in a steady state is very difficult to drive a complete system far from equilibrium, at least a normal matter. A superconductor maybe is slightly more simple because interaction with the lattice is slower, but I mean, in general, it's not so simple. So we will deal always with the quasi-equilibrium. So we need thermometry. So how do we do thermometry? Thermometry and heating, in order to heat one part of the circuit with respect to the other, is done thanks to coupling our regions of interest. Okay, here we have the core of the device. The core of the device is the one which is sensitive to the phase, okay, to the flux. And the other part are the reservoirs, so the source and drain, where we impose, for instance, a chosen temperature that we decided will. So we create a thermal flux flow into the system, and then on the other system we go to measure the other temperature, okay? And how we do this? We tunnel couple typically superconducting tunnel junction, NIS junction, okay, that act as a heater or as thermometer, okay? In the case where we want to probe the temperature on a superconductor, we can deal in a similar way. We use another superconductor, typically, or with similar or different gaps, still tunnel coupled. And from the characteristic of all this kind of object here, we can extract from the electric characteristic, there is a direct response and information on the electronic temperature established in these reservoirs. So I'm just giving some very basic concept of how is electric transport in order that we can understand how do we do thermometry. So if we take the very basic normal metal insulator superconducting junction, okay, here is shown the electric current versus voltage, okay, different temperatures. So you see at the low temperature there is a gap. Here there is a strong current suppression in the presence of the superconducting gap, and then by increasing the temperature we increase the number of quasi-particles, and so we smoothen the curves, okay? How is it operated typically? From this we see that it is very important. The characteristic of an NIS junction basically depends only on the temperature of electronic temperature of the normal metal reservoir, sufficiently low temperature, okay, not on the temperature of the superconductor. So what is nice is a function of temperature. You can have this very sharp features, okay, with a very rapid slope, okay. So you see that, for instance, for large current bias across the junction, there is an important response at higher temperature, whereas if we reduce the current across the system, we have a very sensitive response at the lowest temperature, okay. So in some sense, this thermometer is nice because according to the current that we put inside, we can decide the range of operation where it is more sensitive or less sensitive, okay? And then, of course, what is important is that the thermometer has to be operated in a suitable way that it does not overheat too much the system, because, of course, we want to perturb the system in the smaller possible way in order not to alter all the rest of the physics that we wish to investigate, okay? So this is a very sensitive electrothermometry. If we want to make a classification of this thermometer, I would say that it is not an absolute thermometer, okay, because it relies on the superconducting energy gap in density of states. But if we have calibrated this, it becomes a sort of primary thermometer. So what we do typically is to make a calibration in every experiment against the thermometer of existing in the fridge, okay? So we go down in temperature, we calibrate this curve here with the thermometer in the fridge, and then so our thermometer becomes a sort of absolute thermometer that is in situ. It can be used in every structure you can have how many thermometers you wish, okay? And so to measure different positions and different reservoirs. So this is the concept. The same can be done with superconducting tunnel, fully superconducting tunnel junctions, taking SIS junction, taking advantage. So there are two modes of operation. One is by exploiting the strong feature appearing in the quasi-particle current of an SIS junction. So this is the well-known quasi-particle currents. You see these peaks come out. These are the logarithmic singularity appearing, the difference of the gaps of the two superconductors composing the junction. So one can take advantage of this very sharp structure that appears to make thermometry. And there is a second way of operation, that is the Josephson regime. So basically working at zero bias and studying the temperature behavior of the Josephson coupling. Okay, this is shown here for different configuration. And at sufficiently high temperature, this becomes you see very slope, so the slope is very high, so it becomes a very sensitive thermometer in superconductors. And what is nice, that a Josephson thermometer, by definition, is basically a non-dissipative thermometer because it is operating at zero bias, so, and it's fully dissipationless thermometry. So in some sense, this can be a very useful system to perform thermometry, okay? So basically, we in this kind of research, people uses both of kind of thermometry in the same structure. Depends on which part we are interested in. Okay, so as I was saying, what the important stuff is to define a temperature. Okay, so we are in a quasi-equilibrium regime. There is how is the scheme? This is a very simplified cartoon of a normal superconducting film deposited on top of a substrate. So we inject some heat current inside, so by heating the system. So the electronic temperature can be defined thanks to large electron-electron interaction. And then there is, for instance, there are losses, okay? The losses, the difficult stuff to measure dealing with thermal current, thermal transport is that while in electric transport the charge is conserved in a conductor, here the heat current is conserved in toto, in general, so everywhere. So we have losses everywhere, so in the universe. So the ability to deal with thermal transport is to understand where are the losses and how to quantify the losses existing in the system. This is the point. So the main loss in metals in superconducting system in solid state structure is due to electron phonon coupling. Okay, so the the interaction between the electrons and the phonon of the lattice. Okay, and then there is also the metal film is deposited on top of a substrate. So there is an additional interaction, it is due the interface resistance, so the well-known Kapitsa resistance. Okay, typically, I mean, there is these two, so this ensures that depending on how large is the Kapitsa resistance, the temperature of the substrate can be different from the rate of the phonons in the system. Okay, but typically, I mean, on very small structure, these are almost equivalent. So we are dealing basically, we make the assumption that typically the phonons temperature coincide with the bath temperatures, and the electronic temperature can be completely different from this one. If we look at this kind of interaction, so the electron-phonon interaction, in metal, this is basically dominated by the deformation, is determined by the deformation potential, okay? Whereas, for instance, in semiconductors has completely different nature. For instance, in 3,5 alloys like gallium arsenide, indium arsenide, the electron-phonon interaction is determined by piezoelectric coupling. And in metal and superconductor is typically the dominant one. I mean, the piezoelectric contribution is very small, so it's due to the formation potential. So depending on which kind of metal we are using, there are some very well-known power laws. So this heat current, for instance, is plotted here as a function of the temperature. Okay, the yellow one is the behavior for a clean metal that goes like T to the 5th power. For a disordered metal like aluminum manganese, for instance, this goes like T to the 6th power. A typical clean metal, let's say, that obeys to this law is silver or copper. Okay, polycrystalline films of copper or silver, they obey to T to the 5th power. Okay, and then there is another very important animal that is a superconductor. So in a superconductor, there is a completely different behavior of the electron-phonon interaction, because in this case, there is a gap. It's a gapped system. There is a gap in the density of states. There is a condensation that gives rise to the phase transition. And so the electron-phonon coupling can be extremely weak and can be vanishingly small at low temperature. Okay, so this can be an advantage and disadvantage. Okay, in the sense that the superconductor can be extremely easily overheated, overcooled. So this is why probably the qubits have problems maybe with superconductor, because it's very difficult to remove, and whenever you go to measure them and to touch them, you create quasi-particle and you overheat them. This is the point. But this is because there is so one has to invent efficient techniques to remove quasi-particle, because electron-phonon coupling is pretty weak. Okay, so just one slide about nanofabrication techniques. So all these systems are done typically with made on substrate made of silicon oxide or sapphire. We use suspended mask made of polymethyl methacrylate PMA, and then with the electron beam lithography, one design suitable structure. We use several angle evaporation, so to make shift in the structures, and then oxidation, and then one is able to perform complicated and exotic structure exploiting different materials, from normal metals to superconductors and so forth, so on. So all the structure that I will show to you are realized using this kind of technique here. So as I was saying, the principle of phase dependence, so let's go back to the experiment now. So the idea is to use the macroscopic quantum phase in order to control the heat current flowing in the system. And our toolbox will be the Josephson junction, a standard Josephson tunnel junction. So a temperature biased Josephson tunnel junction. So two superconductors separated by an insulated tunnel barrier and residing at different temperatures. Okay. In the system here, it was predicted in 1965, just after the discovery of the Josephson effect, that the heat current is phase dependent and stationary. Okay, so the idea was first of all to demonstrate this, because up to 2012 it was not clear if this was just a theoretical speculation or there was really the counterpart of the electric Josephson effect. Okay, so at that time I was very interested in. I started to be interested in this kind of things, and I was interested in trying to understand if it was true or not the existence of this term. So we started basically understanding what is going on in the system. So if you write down what is the heat current flowing in a temperature biased Josephson junction, we call the heat current Q total or Q dot total. Okay, we have two different temperatures, and it's composed by two parts. One that is the quasi-particle part, the conventional part, it just depends on the temperature of the two objects. And then there is one additional part that is a phase-dependent part. Okay, the phase-dependent part has a minus. This minus is typical of a tunnel junction. If we had a transparent weak link, there would be a plus and a much more complicated expression as a function of the phase. And for a tunnel junction, it's very simple because this heat current, the phase-dependent parts depends on the cosine. So it's very simple. Okay, so you have a phase-independent part and then a phase-dependent part whose amplitude is just phase-independent, can be factorized in this way, that is superimposed on top of this phase-independent part. The quasi-particle part is very simple. It's just the energy current flowing in the system. It's just the convolution of the density of states of the superconductors and the difference in distribution function. So here they enter just the density of states of the two superconductors. In the, let's call the interference part, this is due to energy carrying processes, due to creation and destruction of Cooper pairs inside the system, which recombine the system from one side to the other in the presence of a thermal bias, and in this process they carry the phase. Okay, so this becomes a fully phase-dependent thermal process. Okay, and I mean, if we think to the language of superconductivity, the Josephson effect, this is just the component of the heat current due to bogolons. Okay, the bogolons are just these excitations that provide information about the phase of the system. So I will not go into detail of this, but in analogy to the quasi-particle part, this is expressed in terms of the density of Cooper pairs in the system in one part, in the other part, times the difference distribution function. What is important to recall is that if the temperatures are identical, of course, there is no heat current of the system. You can say, okay, this is trivial, of course, so both of them are zero. But the interference part is not sufficient that, I mean, the interference part can be zero if one of them is in the normal state. But there is also another condition you need. So you need that both of them are in the superconducting state and there is Josephson coupling. So this is important because without Josephson coupling, you have any phase-dependent part. So the phase-dependent part is basically the analogous of the charge Josephson effect in a purely current bias Josephson junction. Okay, so the point is that okay, now we have a junction in this way. It would be nice to explore the system. So one can ask what is going on in a temperature bias grid. The stuff is very simple because one can easily think to a structure of the system that is what we did, okay, in the experiment, and just combine and to solve the system so that the total current, heat current in the system is just the sum of the two currents flowing the two branches of the slit of the interferometer. And then just by imposing the fluxoid quantization and the critical current, the electric current conservation in the system, we can realize, we can solve fully the system, okay, and realize that the interference part has a shape that is a form in the equation that is identical to the expression for the electric critical current for a DC squid. Here R represents the imbalance between the two junctions, okay? When the squid is symmetric, so when the junctions are identical, you obtain that the heat current, the phase-dependent part of the heat current oscillates as the absolute value of the cosine, so identically to the charge in a charged squid. So if we look at what is going on in terms of this interference part, so being identical to the charge one, the charge counterpart, we can say that when there is, you see, now we just by modulating the flux, we obtain that the interference part is oscillating as the absolute value of the cosine when there is ideality in the interferometer. So there is a maximum visibility, a maximum oscillation. Whereas it tends to a smooth oscillation and then no oscillation at all by increasing the asymmetry of the system. Okay. Then if we look at what is going on in terms of the full heat current, so the quasi-particle and the plus the phase-dependent part, it has a quite complicated behavior in general because you see, I mean, to a low temperature, I mean, there is basically almost vanishing small, and to achieve a sufficiently large heat current, you have to create a larger gradient in the system. So typically, you have to well go in the nonlinear regime of the system in terms of temperatures. And then you see there is of course, you increase by increasing the temperature. If you block one of the two and you increase the temperature of the other, you can have very large oscillation. At the end, they start to decrease because one of the two caps starts to become smaller, and eventually, when we reach the critical temperature of the one, it is no more phase sensitive. Okay, so as we said, it's clear. I mean, this is what to keep in mind. So the total heat current is twice the quasi-particle part minus twice the interference part, let's say. Okay, the minus means that it can be immediately interpreted in an anthropomorphic way, saying that the interference part is flowing in opposite direction with respect to thermal gradient. Okay, so this is very interesting. So this part here, for phase is equal to 0, you see that it is flowing from the colder to the hotter. Of course, we are not violating the principle of thermodynamics. So the full heat current will be always positive and flowing from the red to the blue. Then it's possible to realize some junction where we can invert this sign here. So to realize a pi Josephson junction. So where indeed this term here can completely full rotated by pi. And so also the interference component will fall from the hotter to the colder. So the idea was to realize this kind of interferometer to show the existence of this effect. And so this is the very first device. You see, so I mean, it's composed by a superconducting part. It is, I mean, the fork is a superconductor. Here we have the colder part. And we have some source and drain electrode connected to this island here, comprising heaters and thermometers, where we can create a heat current in this part here by overheating this source and create a thermal gradient between this part, the red and the blue. So this will set up a phase-dependent part like this that possibly, as a function of the flux, will start to oscillate. And so the amount of heat current transferred to the drain, that is the reading part of the circuit, will oscillate as a function of the phase. Okay? So it's very simple. For phase equal to 0, of course, this is minimized. So there is a less flow from the red to the blue part, and so there will be a maximum in the temperature of electronic temperature here, and for half integral values there will be a minimum. So this is what we observed basically. You see that there are several traces at different level of temperature in the normal metal drain. Here is the flux, here is the temperature in the drain. Okay, you see a nice oscillation of temperatures that show the periodicity, phi 0 periodicity, with the maximum for integral values and minimum for half integral values of the flux. Okay, by increasing the temperature leads to an enhancement of the amplitude that we are saying before, that tend to saturate. Here we obtain the maximum 21 millikelvin, that corresponds to 9% of relative modulation amplitude. Okay, then I mean the experiment was performed by looking at the evolution of the visibility, so the amplitude, the swing as a function of the temperature of the source and the average temperature. So okay, they tended to saturate at a larger temperature. Then I mean one important thing is to understand how to manage the theory of the system. So I mean a very simplified way is to consider a system, I mean, in a steady state. So to solve a system of a couple thermal equation, in some sense, balance equation for each reservoir that forms the structure, and setting that the sum of all incoming and outgoing heat sources is equal to 0 at steady state. Okay, so it is a way to create an educated system of thermal integral linear integral equation for all this kind of process here. The result, so we can obtain the electronic temperature in the different parts of the structure and then make the comparison with the system. So for instance, in this case here, the yellow line is the result of these equations, okay, at the steady state with the parameter extracted from the experiment. And so you see that there is a nice, pretty nice accord with the experiment, okay. So this shows that all this transfer Hamiltonian approach that was envisioned by Mackey and Griffin in '65 indeed works pretty well, and indeed there is the existence of this effect. So this can predict very well and modelize very well the thermal Josephson effect. Then, I mean, as happened with the electric Josephson effect, we wanted to probe electric versus thermal quantum diffraction. Okay, so probably many of you knows that in a long, in extended Josephson junction with an in-plane magnetic field, it's possible to observe diffraction pattern in beating pattern in the critical quantum behavior. Okay, this is because the phase accumulates and then create a sort of interference with itself. Okay, and the idea was to show that also for a thermal system, so a thermally biased extended Josephson junction, one could have a sort of diffraction of thermal current in the system. Okay, and it is the same. It happens in the same way. So if one solve the problem theoretically for an extended Josephson junction, depends on the geometry, rectangular, circular, round, or whatever. I mean, the electric critical current is just a Fourier transform of the critical current density along the y direction. Okay, and one can demonstrate that the phase-dependent part of the heat current has almost the same shape. Okay, so for a rectangular junction, there is a very well celebrated Fraunhofer pattern, the sine cardinal. Okay, where the minima appears at integral values, and then there is this fading. Okay, and so for heat should be the same. So the idea was to realize a sort of diffractor, so where the geometry is similar to the previous experiment. We have just one single slit interferometer, rectangular Josephson junction in the presence of field. So we heat one part of the junction. We have interference in the junction itself, and then we monitor here the result of this interference. Okay, so if we look at the Josephson current, electric current, the junction is behaving well. So it behaves like a Fraunhofer diffractor in some sense. If we look at the heat, it's even more impressive because you see, we start from low temperature. Okay, here is the flux to the junction, and then we increase. Of course, we set the temperature bias. Then we increase the temperature in the source. And you see that we increase the general level of current flow, and then it starts to develop these small lumps, lateral lumps that exactly they correspond to this beating of and the Fraunhofer pattern inside the junction. Okay, so this is basically this confirms the second aspect, that is diffraction of thermal currents in a Josephson junction. Okay. Okay. So let's go on. Now I'm trying to give you a quick picture of what has been doing in the years. We have seen that in order to have a nice interferometer, is well known for all people working with squids. Okay, the squid typically works well if it is quite symmetric, because if you lose symmetry in the junction, you lose visibility, so capacity of making interference in some sense. The same is with the heat. So one trick is if one can think to a system that is by construction not very ideal in some sense, but if you replace one of the junction with a second DC squid, there is a way to have, it can be demonstrated that there is a way to have always a perfect balancing of the system anyway, in any case. If, for instance, the critical current, let's say the resistance of one junction, satisfy a relation with the critical current that flowing in one junction is comprised between the difference the sum of the two. So in this case, it's always possible to have the full compensation, so the suppression of the interference part. So in our case, the suppression to zero of the phase-dependent part. And in some sense, this system here can be also interesting, because if we plan to use the two fluxes in a time-dependent fashion, this could lead to quantum heat pumping or time-dependent heat engine. So this would be the way to implement thermal machines at the nanoscale. Okay. So the idea was basically the following. In this case, the idea was to try to show that in a fully unbalanced by construction interferometer, it's possible at the end to have the full suppression of the supercurrent. So we realized a sort of multi-loop. In this case, it was a double loop system. So the system was similar to the first result, the first experiment, but thanks to this very different ratio between the two areas of the interferometer, you see you have very complicated beating patterns of the Josephson electric current, Josephson critical current. Okay, so thanks to this difference in the area. Okay, but you see, I mean, this at least from the electrical point of view, they can be easily fitted. I mean, with RSJ models, resistivity and shunt and capacitive model for the junction. So you see that the line, the black line, is the fit to the data. So in some sense, one can take very precisely into account the difference of the interferometer. Okay. What is important is that from the electrical point of view, it was possible to annihilate the critical current down to 99%. And there was a huge asymmetry between the two junctions. Okay, but this is well known. I mean, from the electric point of view, we want to demonstrate it was possible to do the same in the electric case. So in the thermal case. So in the thermal case, by doing the same kind of experiment as before, it was possible, I mean, to see that the electric temperature, you see how complicated behavior follows, but basically mimics the electric one. So all these are beatings of the electric temperature in the simply as a function of the flux. Here we got very nice 40 millikelvin temperature swing. So we doubled what we obtained in the first experiment. And from our theoretical model that it was again an educated guess of how all the thermal losses behave in the system, we were able to demonstrate. You see here are the fit to the temperature oscillation, that the interference part can be suppressed of the heat carrier in the same way as 99%. So this basically shows that whatever complicated shapes of multi-loop interferometers you can conceive electrically, this can be replicated in the thermal world, in the energy world, by taking into account, I mean, how the system is exchanging with the rest. So it's a full demonstration that it's possible to do in the same way. Okay. Now that we have seen basically how interferometers do behave, there's another important issue, is that we have introduced all the arguments saying that the interference, the phase-dependent part in a junction, flows in opposite direction with respect to the thermal gradient. Okay, so the phase-dependent part is always smaller and flows in the opposite direction. It would be nice to realize a system where, with the ability to change the sign of this component in order to play at will with the heat current in the system, okay? But you can imagine that this is not so simple. So, I mean, this is basically the implementation of the thermal version of the pi Josephson junction, where in a pi Josephson junction, indeed, the critical current flows in opposite direction with respect to the phase gradient. So how can we do this structure here? The structure here can be realized in a way, in a sort of, by implementing a sort of pseudo radio frequency squid. So a squid where we have three different junctions, and taking into account that if we make the junction of interest, that is the phi j, with resistance much larger than the other, so that each critical current dominates the full phase landscape of this guy here, all the phase drop will always fall at this junction here. So thanks to y for phase equal to 0, flux equal to 0, there is zero phase across this junction here. So the heat current will flow in the opposite direction. For 1/2 phi naught, for instance, we will have pi across this junction here. So this will permit to rotate completely the phase and to have the junction, the heat current in the same direction. Okay, so this is the implementation of the system. This is more complicated. There is is fully superconducting structure in this case. Okay, and we have implemented the junction where this junction here, that is where we obtain the full rotation, has a much larger resistance than the other two, so that all the phase drop occurs here, and we are able to completely phase tune the interferometer from 0 to pi. Okay. And if you look at this, what is nice is that in this kind of interferometer, we obtain the record temperature oscillation up to 100 millikelvin, because, of course, you can add also the other components. So by changing the sign, we can increase enormously the full amount of heat that is transferred from one part to the other. And thanks to the superconducting nature of the structure, we were able to obtain very large temperature oscillation up to 800 milliK, because due to the fact that the electron-phonon coupling is extremely weak also at higher temperature in a superconducting state. So this guy here at the end was basically it was very interesting and important, because in a system where you can achieve a full rotation of pi, in this sense, is the way to achieve what is known as negative differential thermoresistance. So it's the equivalent of the resonant tunneling diode in the electron transport. So when in SIS system you can rotate the phase pi, you can achieve this regime of negative differential thermoresistance. So by increasing the temperature, you decrease the thermoresistance. And so this is a way to construct future heat amplifier, for instance. Okay, so now we'll go towards the last stuff, that is routing. So up to now I have shown single output caloritronic devices. Okay, so we started from, so we have just one source and one drain. What is very important in electronics is to have a system where we can divide currents, okay, to make operation on more different blocks. So we started from the Josephson interferometer, diffractors, more complicated multi-loops. I have shown the pi junction. I didn't show the thermorectification because we also perform thermorectification efficiently with superconductors. Okay, but all these devices were single, one input and one output. Okay, very important to show, for instance, if it is possible to do a sort of routing, okay, thermal routing system. So what is a phase tunable router? Is just a system. This is a general scheme. So we have a heat source that goes inside a sink, and then we have a phase tunable object that is able to separate the heat carrier from one side to the other. So to enhance, for instance, the temperature of one drain with respect to the other for integral values of the flux. And for semi-integral value of the flux, for instance, according to all the fields that we have shown, this temperature here, for instance, can be smaller than the other. So in this way, by modulating the flux, we can make, of course, the temperature of one guy to increase and the other to diminish. So you see that the temperature of the object, if we use a squid in this way, if the core of the device is a squid, they will behave in anti-phase, one respect to the other. Okay. And what is interesting, so the system can use a splitter because we can divide the two heat fluxes according to construction parameters. And so the oscillation, so the modulation, the general modulation will be given by the quantum phase mechanism existing in the system. And then there is another possibility to make swapping of the temperature. What is swapping? If we construct well the system, we can make the temperature of one to become larger than the other, okay, at will. And so, I mean, if we think to this in a time-dependent way, this is the way to implement a thermodynamical engine, a real engine. So, in time to change the temperature of one with respect to the other, to start to create cycles. So, I will show that it is possible to do both the splitting and then the swapping of the system, okay? So, this is a very basic idea. So, we start again with a squid, and where we use the source is one arm of the squid that release heat in one drain, and the second part of the squid release heat on the another drain. So this is a two-drain structure. Okay. Here, so there is a source. You see here this interferometer, where the drain 1 and drain 2 are connected to this two parts of the squid, and by manipulating the flux, we are able to control and to make the different temperature between the two and to make them to swap in different regimes. What mainly controls the swapping regime is the electron phonon coupling. So how this, the drain 1 and drain 2 exchange heat with the lattice, whereas the general oscillations is given by the flux, let's say. So if we look at this kind of system, for instance, here, so the thin line is the drain 1 here, and the thick line is drain 2. You see that we start at low temperature with some fixed power inside as a function of the magnetic field in the interferometer. We see that they fully operate in antiphase. Okay, so when one is maximum, the other is minimum, as expected, and they full oscillate. Okay, then by increasing the temperature of the lattice, we increase the electron phonon coupling, and the two temperatures starts to cross, and then there is, you see, a swapping regime when the temperature of the one is larger than the other. This mechanism can be implemented as well by fixing the bus temperature and by changing the amount of power injected here. For instance, we go for low power. This can be explained, of course, with all the relaxation occurring inside. So we go from low power, where there is already a regime where they can swap, up to a larger heat current here, where they are completely separated. Okay. What is interesting is that, for instance, here are just two traces of the two drain 1 and drain 2 at different bath temperature, 400 and 200 milli. So for instance, and 60 picowatt roughly of injection. Here in this range we see that there is a full separation and there is just splitting, okay? And the dashed lines refers to the to the transfer Hamiltonian models of the state balance equation, thermal balance equation to fit that represented. So there is a nice accord, as you see. And you see that by increasing the temperature again, we go in a regime of swapping. And also, the regime of swapping is can be fully taken into account with the same equation. So all this machinery of theory seems to work very well to describe all this heat transfer phenomena in this Josephson system. Okay. And what is interesting, for instance, that in this case here, we are able to obtain a maximum difference in split in temperature of 40 milli at 50 milli, so a very large temperature, in this case difference, and a swap-in temperature of 4 milli, the maximum. So we were obtaining a maximum separation between the two in this swapping regime of 4 milli. Of course, this can be improved by choosing, by improving the parameter, now that we have demonstrated for the first time that it's possible to do this. Okay, so I will go to the conclusions. So apart giving the main concept of the phase control of heat, we have shown the realization of the first heat interferometer that has confirmed the existence, the magnitude and the sign of phase-dependent heat current existing in Josephson systems. Then we have shown the realization of the first quantum diffractor of thermal flux that sets the complementary proof of the thermal Josephson effect in this kind of system. Okay? Then we have shown how double loop or multi-loop Josephson thermal modulators can ensure a complete phase engineering of electronic heat current at the nanoscale. Next step, we have shown that it's possible to implement a 0-pi thermal Josephson junction that represents the analog of the pi junction in electric transport. And finally, have shown the realization of the first phase-tunable Josephson thermal router with large separation and sizable temperature inversion. So we believe that this is the gateway to realize mesoscopic thermal machine working thanks where in the space of the phases of the superconducting elements. Thanks for your attention.